I always thought geology was boring, and I never really cared about it. But I was very wrong, and this is why. So many other sciences, it's kind of like math. So many other sciences use geology as a foundational need and almost as a language. For example, archaeology. When you're doing a dig to find human artifacts, you need to know and understand geology, because you need to understand how to date an artifact, understand how old it is. That requires understanding how old the rock surrounding it was. That doesn't tell you how old the artifact is, but it gives you a very good estimate at a lot of the time, with exception to if something was maybe buried underground intentionally. You need to know, when you're a paleontologist or maybe even a zoologist uncovering fossils, when you're working with fossils, you need to know geology so that you can understand how old that fossil is, how that fossil got there, maybe what type of climate that species lived in. All kinds of stuff that I don't even know about because I don't know geology. I don't understand it. So, on top of that, it is really interesting. Fucking cat is fucking yelling. One moment. I'm just going to ignore it for the time being. So, it's really interesting because it's not just the study of rocks. It's the study of the entire Earth. The entire planet. Do you hear that? I think you hear that. I hope you do, so that you can understand my pain. So, motherfucker. It's the study of the entire Earth. I used to think it was just the study of rocks, and it's like, why do I give a shit about rocks, man? I don't care. But you're studying the Earth's crust. You're studying the Earth's oceans and the floor beneath them. You're understanding how plate tectonics work, earthquakes. You're studying the inner core of the Earth and what's going on down there. You're studying maybe even the weather. I don't know. And you're studying how everything interacts with the planet and how the planet interacts back. It's incredibly important because this is where we all live. And it's also just it's cool. It's a very cool study. I want to know more about this world that we all live on. It's just as interesting to me as the study of the universe, as the study of the quantum realm. Because I would say perhaps even more, but I'm not going to say that. Just because this is real. This is reality. Reality takes place here, first and foremost. And that just makes it very interesting for me. And if you clicked on this video, you probably already think it is, but whatever, bro. So, yeah, it's a prerequisite, and it's also intrinsically valuable and interesting. So, yeah, I found this geology textbook. It was free, online. I literally just Googled geology textbook PDF, and it came up. So, we're just going to start it today. So, what is geology? In its broadest sense, geology is the study of Earth, its interior and its exterior surface, the minerals, rocks, and other materials that are around us, the processes that have resulted in the formation of those materials, the water that flows. That's the other thing. You're not just studying the earth, you're studying. Notice how I said stuttering instead of studying, and it was while I was stuttering. You're studying how the earth came to be. You're studying how it got to where it is right now. Pangea. The fact that Antarctica used to be a tropical place. That's really cool. And everything else that's happened in the billions of years that Earth has existed. And how it got to where it is now, how it got to where it was 2 billion years ago, how it got to where it was 3 billion years ago, and how life arrived on Earth. That is a big part of geology. Why this Earth supports life. Anyway. Its interior and exterior surfaces, the minerals, rocks, and other materials that are around us, the processes that have resulted in the formation of those materials, the water that flows over the surface and through the ground, the changes that have taken place over the vastness of geological time. Yeah, so I was wrong. The study of the weather is meteorology. It's not geology. It's a different thing. And the changes that we can anticipate will take place in the near future. I actually paused the video because I added a meteorology to the list of things that I want to study in my life, because this is just a tangent, but I don't know. I feel like it would be interesting to understand how tornadoes work and how hurricanes work and how, I guess I already know how rain works, but how lightning works and other tropical storms, and also, I don't know, different types of clouds. Am I autistic? I just that thing where people say, ask a question and then they go and then they go silent as a comedic technique, and I didn't like that. I had an urge to edit that out, but I'm gonna keep it in because this video is supposed to be raw and real. So you're just gonna have to sit with that dumbass joke, half joke, awkward ass shit, like an adult. Anyway, also there's weather on other planets. There's weather on Jupiter. There's weather on Neptune. Way more disastrous, incredible, insane, surreal weather. Storms that go on for centuries. I've heard of a planet where it rains glass. I want to know how that works. So interplanetary meteorology. How the fuck is that? What's going on there? Anyway. So, let's continue. Sorry. Geology is a science, meaning that we use deductive reasoning and scientific methods to understand geological problems. It is arguably the most integrated... God damn it, I have to plug in my fucking computer. I'm sorry for all the distractions. Geology is a science, meaning that we use deductive reasoning and scientific methods to understand geological problems. It is arguably the most integrated of all the sciences because it involves the understanding and application of all the other sciences. Physics, chemistry, biology, mathematics, astronomy, and others. That's really cool. Didn't know that. But unlike most of the other sciences, geology has an extra dimension, that of time. Deep time. Billions of years of it. Geologists study the evidence that they see around them, but in most cases, they are observing the results of processes that happened thousands, millions, and even billions of years in the past. Those were processes that took place at incredibly slow rates, millimeters per year to centimeters per year, but because of the amount of time available, they produced massive results. Geology is displayed on a grand scale in mountainous regions, perhaps nowhere better than the Rocky Mountains in Canada. I didn't know the Rocky Mountains went to Canada. I thought they were just in the Colorados. Colorado. There is no Colorados. The peak on the right is the Rearguard Mountain, which is a few... I'll go to the images right here. I'll go to that in a minute. The peak on the right is the Rearguard Mountain, which is a few kilometers northeast of Mount Robson, the tallest peak in the Canadian Rockies. The large God damn. The large glacier in the middle of the photo is the Robson Glacier. The river flowing from the Robson Glacier, excuse me, drains into Berg Lake in the bottom right. There are many geological features portrayed here. Let's go look at this. So, 1.1.1, 111, Rearguard Mountain and Robson Glacier in Mount Robson Provincial Park, BC, British Columbia, I'm guessing. Left is Robson Glacier in 2012. Right is Robson Glacier circa 1908. Interesting. Oh, I see what they're saying. I see what they're doing here. They're pointing out the recession of the glacier here. This is a very large glacier. This is not as large. I see what they're doing. I do believe climate change is another very significant aspect of geology, and I understand some of you probably don't believe in climate change. We're just going to read the textbook. I'm not going to give my 2 cents on it. So yeah, and it flows into this river. I'm guessing that is the Berg River, right? Is that what it said? Berg Lake, drains into Berg Lake. I'm guessing this larger body of water. Oh no, it's this. This is Berg Lake. Berg Lake. Okay. The sedimentary rock that these mountains are made of formed in ocean water over 500 million years ago. A few hundred million years later, these beds were pushed east for tens to hundreds of kilometers by tectonic plate convergence, and also pushed up to thousands of meters above sea level. Over the past 2 million years, this area, like most of the rest of Canada, has been repeatedly glaciated, and the erosional effects of those glaciations are obvious. Okay, all right, so glaciers cause erosion. Did not know that. Don't really know how that works. The Robson Glacier is now only a small remnant of its size during the Little Ice Age of the 15th to 18th centuries. Oh, okay. And even a lot smaller than it was. I'm guessing they mean than it was. Textbooks make a lot more typos than you might think. I've read many a textbook in my life. They make a lot of typos in textbooks. It's weird. Written by humans. Humans make mistakes. Funny. You'd think they'd double check it though. It makes me a little unsure. Even a lot smaller than it was just over a century ago in 1908. You'd think somebody would catch it. Sorry. The distinctive line on the slope on the left side of both photos shows the elevation of the edge of the glacier a few hundred years ago. The distinctive line on the slope. What distinctive line on the slope? I don't see this thing right here. This business. Is it that? Maybe. On the left side of both photos, yeah. I don't really know what they're talking about. I'm having a little trouble. I'm having a little bit of trouble. Yeah, it shows the elevation of the edge of the glacier a few hundred years ago. Like almost all other glaciers in the world, it receded after the 18th century because of natural climate change. Natural climate change is now receding even more rapidly because of human-caused climate change. Okay, interesting. See, it seems that most controversy surrounding climate change separates it between natural and human-caused. There's a big party that does agree that natural climate change is a thing and that human-caused climate change is not. This textbook seems to be arguing that both are true, both exist. I do believe that is more so the position of the liberals. Yeah. So you could consider this a liberal textbook. I don't know. I'm going to take everything it says with a grain of salt like I always do. I feel like if a conservative person was watching me, they would be thinking to themselves, wow, this person is getting indoctrinated with liberal beliefs. I'm taking it all with a grain of salt. So I'm just going to stop talking about controversial topics right now, other than what the textbook has to say. Because of natural climate change is now receding even now. I'm sorry. I do think that the conservative belief about climate change might be a little bit flawed because of the fact that it only considers natural climate change. And it argues that natural climate change is all that's happening as of recently. I do think that belief could be flawed, but I can't prove them wrong. I'm not knowledgeable enough to prove them wrong. I'm not going to act like I really know my shit about this topic. I don't know anything about this topic. Anyway, let's continue to the book. Now receding even more rapidly because of human-caused climate change. And we already looked at this. Geology is also about understanding the evolution of life on Earth, about discovering resources such as water, metals, and energy, about recognizing and minimizing the environmental implications of our use of those resources, and about learning how to mitigate the hazards related to earthquakes, volcanic eruptions, and slope failures. Does that mean landslides? Slope failures? All of these aspects of geology and many more are covered in this textbook. What are scientific methods? Should we read this? Do we need to read this? Maybe. Let's try, and if we figure we don't need to after reading some of it, we'll just move forward. There is no single method of inquiry that is specifically the scientific method. Furthermore, the scientific inquiry is not necessarily different from serious research in other disciplines. The most important thing that those involved in any type of inquiry must do is to be skeptical. As the physicist Richard Feynman once said, the first principle of science is that you must not fool yourself, and you are the easiest person to fool. A key feature of serious inquiry is the creation of a hypothesis, a tentative explanation that could explain the observations that have been made, and then the formulation and testing by experimentation of one or more predictions that follow from that hypothesis. For example, we might observe that most of the cobbles in a stream bed, this is where geology relates to the scientific method, we might we might observe that most of the cobbles in a stream bed are well-rounded. See photo above. Fairly well-rounded, I guess. And then derive the hypothesis that rocks are rounded by transportation along the stream bed. A prediction that follows from this hypothesis is that cobbles present in a stream will become increasingly rounded as they are transported downstream. An experiment to test this prediction would be to place some angular cobbles in a stream, label them so that we can be sure to find them again later, and then return at various time intervals over a period of years to carefully measure their locations and roundness. I'm guessing if you're only doing a period of years, obviously you can't do a period of hundreds of years unless you do an insanely, incredibly long study that's the length that we've never even tried before. You could give that a go, but that's a really difficult study to do. So if you can really measure the smoothness of the rock very carefully, you could notice small changes to make the study shorter. A critical feature of a good hypothesis and any resulting predictions is that they must be testable. For example, an alternative hypothesis to the one above is that an extraterrestrial organization creates rounded cobbles and places them in streams when nobody is looking. This may indeed be the case, but there is no practical way to test this hypothesis. Most importantly, there is no way to prove that it is false, because if we aren't able to catch the aliens at work, we still won't know if they did it. That's kind of interesting. That's kind of funny. 1-2. Why study Earth? We're already 5 pages into this shit, by the way. It's kind of cool. The simple answer to this question is that the Earth is our home, our only home for the foreseeable future, and in order to ensure that it continues to be a great place to live, we need to understand how it works. Another answer is that some of us can't help but study it because it's fascinating. That would be more so my motive. But there is more to it than that. We rely on the Earth for valuable resources such as soil, water, metals, industrial minerals, and energy, and we need to know how to find these resources and exploit them sustainably. We can study rocks and the fossils they contain to understand the evolution of our environment and the life within it. We can learn to minimize our risks from earthquakes, volcanoes, slope failures, and damaging storms. We can learn how and why Earth's climate has changed naturally in the past, and use that knowledge to understand both natural and human-caused climate change. We can recognize how our activities have altered the environment in many ways and the climate in increasingly serious ways, and how to avoid more severe changes in the future. We can use our knowledge of Earth to understand other planets in our solar system, as well as those around distant stars. That is a very, very interesting part of geology, is the idea that geology can transfer from one planet to another. That's really cool. And even stars, which aren't planets, but are still celestial bodies, and even moons. I can imagine. Like, what's underneath the moon? Is the moon similar to the Earth in the sense that it has crust and maybe a core beneath it? What's at the core of the moon? What's going on there? An example of the importance of geological studies for minimizing risks to the public is illustrated in Figure 121. This is a slope failure that took place in January 2005 in the Riverside Drive area of North Vancouver. The steep bank beneath the house shown gave way, and a slurry of mud and sand flowed down, destroying another house below and killing one person. This event took place following a heavy rainfall, which is a common occurrence in southwestern BC in the winter. Wow, look at that. Aftermath of a deadly debris flow in the Riverside Drive area of North Vancouver in January 2005. That is nuts. That looks bad. I wish there was a video we could watch, but I'm guessing there isn't, and frankly, that would probably count as a snuff video, because people died. I don't know why I'm laughing about that. Not funny. It's just more of a laugh in awe. Like when you laugh when you see an absurdly incredible looking church. Not that I think it's a good thing that happened. I hope you know what I mean. Like, it's just absurd. Like, I'm in awe of that happening. In the same way I would be in awe of seeing a hurricane or seeing a tornado. I'd be like, that is insane. Just don't want you to think I'm a psychopath. The irony of the 2005 slope failure is that the District of North Vancouver had been warned in a geological report written in 1980 that this area was prone to slope failure and that steps should be taken to minimize the risk to residents. Very little was done in the intervening 25 years, and the consequences of that were deadly. 1.3. What do geologists do? Geologists are involved in a range of widely varying occupations with one thing in common: the privilege and responsibility of studying this fascinating planet. In Canada, many geologists work in the resource industries. I wonder if the person who wrote this book was in Canada, because they're referencing a lot of Canadian stuff. Many geologists work in the resource industries, including mineral exploration and mining, and energy exploration and extraction. Other major areas where geologists work include hazard assessment and mitigation, e.g., assessment of risks from slope failures, earthquakes, and volcanic eruptions. Supply planning. Oh my god, I'm a fucking idiot. I just said supply. Water supply planning, development, and management. Waste management, and assessment of geological issues in the forest industry and on construction projects such as highways, tunnels, and bridges. Most geologists are employed in the private sector, but many work for government-funded geological organizations, such as the Geological Survey of Canada or one of the provincial geological surveys. And of course, many geologists are involved in education at the secondary and post-secondary levels, so master's and PhD. I feel like I'm doing a shitty job at popcorn reading right now. I'm stumbling over my words. Like, if I was in a classroom and we were doing popcorn reading, I would feel like an idiot, you know? Like when you get selected for the popcorn reading and you just do a shitty job and everybody's correcting you. Some people are attracted to geology because they like to be outdoors, and it is true that many geological opportunities involve field work in places that are as amazing to see as they are interesting to study. But a lot of geological work is also done in offices or laboratories. Geological work tends to be varied and challenging, and for these reasons and many others, geologists are among those who are the most satisfied with their employment. Yeah, I'm not surprised. This seems incredibly satisfying, rewarding, intrinsically valuable. 131, geologists examining ash layer deposits at Kilauea, would that be right? Volcano, Hawaii. So are these ash layer deposits right here? Don't know. Right. In Canada, most working geologists are required to be registered with an association of professional geoscientists. This typically involves meeting, this textbook was definitely written in Canada by a Canadian resident, perhaps even 4 Canadians. This typically involves meeting specific, post-secondary educational standards and gaining several years of relevant professional experience under the supervision of a registered geoscientist. More information can be found at Engineers and Geoscientists, British Columbia. 1.4 Minerals and Rocks. We're almost halfway through this chapter, which is amazing. We might finish the whole chapter by the end of the video. The rest of this chapter is devoted to a brief overview of a few of the important aspects of physical geology, starting with minerals and rocks. This is followed by a review of Earth's internal structure and the processes of plate tectonics, and explanation of geological time. The Earth is made up of varying proportions of the 90 naturally occurring elements: hydrogen, carbon, and I believe there are more than 90 elements on the periodic table, so a lot of them, I guess, would be from a lab, like created in a lab assisted, something like that. Hydrogen, carbon, oxygen, magnesium, silicon, iron, and so on. In most geological materials, these combine in various ways to make minerals. Minerals will be covered in some detail in Chapter 2, but here we will briefly touch on what minerals are and how they are related to rocks. A mineral is a naturally occurring combination of the specific elements that are arranged in a particular... Hold up, let's read that again. A mineral is a naturally occurring combination of specific elements that are arranged in a particular repeating 3-dimensional structure or lattice, if I'm saying that right. The mineral halite, or I'm guessing I'm saying that right, is shown as an example in figure 141. Is this it? Yeah. Oh, halite, also known as salt, sodium chloride. Figure 141, the lattice structure and composition of the mineral halite, common table salt. Interesting. This would be a compound in chemistry. Very interesting. I didn't know that this was what a structure of a compound looked like, or at least this compound. In this case, atoms of sodium alternate with atoms of chlorine in all 3 dimensions, and the angles between the bonds are all 90 degrees, even in a tiny crystal like the ones in your salt shaker. The lattices extend in all 3 directions for thousands of repetitions. Halite always has this composition and this structure. Interesting. So there are 90-degree angles at the atomic level. 90-degree angles. It is surreal how perfect that looks. I mean, I'm guessing it looks different in the real world, in reality, but they are saying they are 90 degrees. That's insane. That's so cool. Note, element symbols are used extensively in this book. In Appendix 1, you'll find a list of the symbols and names, blah, 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 blah. There are thousands of minerals, although only a few dozen are mentioned in this book. In nature, minerals are found in rocks, and the vast majority of rocks are composed of at least a few different minerals. A close-up view of granite, a common rock, is shown in figure 142. I'm guessing that's this. Although you probably didn't see that. I'm guessing that's this. Although a hand-sized piece of granite may have thousands of individual mineral crystals in it, there are typically only a few different minerals, as shown here. Okay. So this is granite. Very interesting. Figure 142, a close-up view of the rock granite and some of the minerals that it typically contains. H is hornblende, amphibole, Q is quartz, and F is feldspar. The crystals range from about 0.1 to 3 millimeters in diameter. Most are irregular in outline, but some are rectangular. All right, so we have, what is F? Feldspar. So this is feldspar, seems lighter, although this one is more yellow. That is more yellow. H would be what? Hornblende. Hornblende. And then we got quartz right here, and right here, and right here, which is darker than I would imagine it to be. I wonder why. Rocks can form in a variety of ways. Igneous rocks form from magma, molten rock, that has either cooled slowly underground, e.g. to produce granite, so I guess granite is a type of igneous rock, or cooled quickly at the surface after a volcanic eruption, e.g. basalt. Sedimentary rocks, such as sandstone, form when the weathered products of other rocks accumulate at the surface and are then buried by other sediments. So, to break down sedimentary rocks, I guess it's like erosion from water causes sediment to break down from other rock, maybe? Yeah, other rocks. And then that sediment accumulates, kind of maybe in a mud sort of texture. And then it gets covered by another layer of sediment, and then that eventually creates rock. That is very interesting. Metamorphic rocks form when either igneous or sedimentary rocks are heated and squeezed to the point where some of their minerals are unstable, and new minerals form to create a different type of rock. An example is schist. Would that be correct? Pronunciation. A critical point, we're halfway through now. A critical point to remember is that the difference, or maybe a page away from halfway through, it's a bit of a one-off error from me, I think. A critical point to remember is the difference between a mineral and a rock. A mineral is a pure substance with a specific composition and structure, while a rock is typically a mixture of several different minerals, although a few types of rock may include only one type of mineral. Examples of minerals are feldspar, quartz, mica, halite, calcite, and amphibole. I gotta burp. It's coming. Well, I don't know. It's kind of sitting there. I don't know. Examples of rocks are granite, basalt, I spit again, sandstone, limestone, and schist. All right. Key takeaway, know the difference between minerals and rocks. If you're currently taking a geology course, you'll likely be asked more than once to name a mineral or a rock that has specific characteristics or composition, or was formed in a specific environment. Please make sure that if you're asked for a rock name, that you don't respond with a mineral name and vice versa. Blah, blah, blah. Exercise 1.1. Find a piece of granite. The rock granite is very common in most parts of North America, and unless everything is currently covered with snow where you live, you should have no trouble finding a sample of it near you. The best places to look are pebbly ocean or lake beaches, a gravel bar of a creek or river, a gravel driveway. I wonder how a gravel bar comes to formation. Would that be human created? I would guess not. I would guess that it is created from the cat is crying again. Do I do something about it? I feel like I should. I guess we'll see how long it goes. I'm gonna close my ears. She has everything she needs. I just want to make that clear. She has everything she needs. She's just pissed. She's bored. Abby's in there. My fiance is in there. She has no reason to be complaining, other than the fact that she might be bored. Yeah, I don't know how these would be formed. Like, I have no idea. I'm guessing it's either some kind of natural process or it is... I'm guessing it's a natural process because it's by water. So I'm guessing like that's kind of stones that form from maybe they're sediment. Maybe that counts as sediment. I don't know. A gravel driveway or somewhere where gravel has been used in landscaping. In figure 143, taken on a beach, the granitic pebbles are the ones that are predominantly light colored with dark specks. The one in the very center is a good example. This would be, yeah, this is gravel, and I'm guessing this is granite right here. It is light with darker specks. Maybe this is granite right here. I don't know. It also is specks, but it's more dark with white specks. But it could count. Select a sample of granite and, referring to figure 142, see if you can identify some of the minerals in it. Let's see. This looks like granite. The white stuff might be, what would that be? That would be the H, right? Hornblende. No, the H is the black. The white, it would be F. That would be feldspar, maybe. Let's see. Feldspar would be maybe the white stuff, I would guess, and the darker stuff would be H, hornblende, and maybe the grayish stuff would be quartz, or maybe some of the white stuff. I don't know. See if you can identify some of the minerals in it, blah, 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 blah. It may help to break it in half with a hammer to see a fresh surface, but be careful to protect your eyes if you do so. You should be able to see glassy-looking quartz, dull white plagioclase feldspar. I doubt I'm pronouncing that right. And maybe pink potassium feldspar. And black hornblende, or in some places, flaky black biotite mica, or both. In addition to identifying the minerals in your granite, you might also try to describe the texture in terms of the range sizes of the mineral crystals. In millimeters. What? And the shapes of the crystals. Some may be rectangular in outline. Most will be irregular. Think about where your granite might have come from and how it got to where you found it. Obviously, we're not going to do this right now. I'm at a desk, but maybe I'll do this at some point once I stumble upon some type of place where there is gravel, or like a bed of gravel by a stream or a river. I don't know. Yeah, maybe I'll make a video about this in the future. 1.5 Fundamentals of Plate Tectonics. Plate tectonics is the model or theory that has been used for the past 60 years to understand and explain how the Earth works. More specifically, the origins of continents and oceans, of folded rocks and mountain ranges, of earthquakes and volcanoes, and of continental drift. Plate tectonics is explained in some detail in Chapter 10, but is introduced here because it includes concepts that are important to many of the topics covered in the next few chapters. Alright. Ooh. Here's the Earth's crust and other layers of the Earth. If we zoom in, we got the lithosphere, which seems to be the area right underneath the crust and before the upper mantle. Don't know what goes on down there. Sorry, let me zoom back in. Alright, let me just reorient that. There we go. Sorry, I have a breathing problem. Got the lower mantle, and then we've got the outer core liquid and the inner core solid. Figure 151, the components of the interior of the Earth. Click on the image to see a full-size version. Whoa, resource not found, so whatever. Oh man, we gotta scroll all the way down. It's fine. Here we go. So, I gotta reorient it again. Forgive me. Key to understanding plate tectonics is an understanding of Earth's internal structure, which is illustrated in figure 151. Earth's core, I think that's what we just looked at. Earth's core consists mostly of iron. The outer core is hot enough for the iron to be liquid. Sorry. The inner core, although even hotter, is under so much pressure that it is solid. I wonder how that works, like pressure making things solid. I want to learn about that at some point, but I'm guessing that's more of a chemistry subject than a geological subject, though I could be wrong. I'm sure there's a lot of interplay there. The mantle is made of iron and magnesium silicate materials. The bulk of the mantle surrounding the outer core is solid rock. Huh. I didn't know that. I figured that the mantle was entirely magma, but I guess I'm wrong. But is plastic enough to be able to flow slowly. Okay, so it's solid, but it has plasticity. Interesting. So it's solid, but not completely solid. The outermost part of the mantle is rigid. The crust, composed mostly of granite. Okay, so the outermost part of the mantle is rigid, so that I'm guessing that means it's doesn't have the plastic properties of the bulk of the mantle. Interesting. I thought the outermost part of the mantle would be magma. That's what I always saw in movies and shit. The crust, composed mostly of granite on the continents. I didn't know that. And mostly of basalt. I feel like it might be basalt or something. I'm an idiot. Is also rigid. The crust and outermost rigid mantle together make up the lithosphere. Oh, okay, so that's what the lithosphere is. So it's not the little piece between the crust and the mantle. The lithosphere is divided into about 20 tectonic plates that move in different directions on the Earth's surface. Only 20. That's interesting. I figured there would be more. I figured there would be way more than 20. That's kind of nuts to me. Only 20. So, for example, like the St. Andreas Fault? That's not St. Andreas. I'm thinking San Andreas. No. What's the GTA called? That's San Andreas, right? It's not San Andreas Fault. I'm dumb. It's something else. But that, you know what I'm talking about, that fault that runs in California that causes so many earthquakes, that separates 2 of the 20 tectonic plates. That's wild. An important property of Earth and other planets is that the temperature increases with depth, from close to 0 degrees Celsius at the surface to about 7,000 degrees Celsius at the center of the core. What would that be in Fahrenheit? Like 30,000 degrees? In the crust, the rate of temperature increase is... Sorry, somebody's opened the door. Where were we? In the crust, the rate of temperature increase is about 30 degrees Celsius every kilometer. You know what? I'm going to let the cat out a little while. Never mind, somebody just went in the bathroom. She's not in the bathroom. It's kind of complicated. Our bedroom is disconnected from the rest of the house by a bathroom. You got to go through the bathroom to get to the bedroom, so I can't get to the bedroom if there's somebody in the bathroom, if that makes sense. Anyway. So, in the crust, the rate of temperature increase is about 30 degrees Celsius every kilometer. This is known as the geothermal gradient. That's interesting that it's so steady like that it's such a predictable increase. I wonder how we know that. Heat is continuously flowing outward from the Earth's interior, and the transfer of heat from the core to the mantle causes convection in the mantle. I forget exactly what convection is. I'm pretty sure it's... isn't that like the exchange of heat through gas? Would I be wrong? Where were we? Fuck, I lost my place. Yeah, here we go. This convection is the primary driving force for the movement of tectonic plates. Really? The movement of tectonic plates is caused mostly by the convection of heat transfer? Like convection heat transfer from the Earth's crust to the mantle and back? That's weird. I did not know that. So, sorry, I keep losing my place. At places where convection currents in the mantle are moving upward, new lithosphere forms at ocean ridges. What? Let me reread that. At places where convection currents in the mantle are moving upward, new lithosphere forms at ocean ridges. What's an ocean ridge? What is that? And the plates move apart, diverge. Where two plates are converging and the convective flow is downward, one plate will be subducted, pushed down into the mantle beneath the other. Many of the Earth's major earthquakes and volcanoes are associated with convergent boundaries. I did know that. Okay. All right. What in the world? So, let me reread this sentence. At places where convection currents in the mantle are moving upward, new lithosphere forms at ocean ridges, and the plates move apart, diverge. So that creates a new, what are they called? A new fault in the crust? What? Okay. All right. So here we have a little diagram. 152, depiction of the convection in the mantle and its relationship. That is not the right way to use its. I hate to be that guy. I don't know if you can see. IT apostrophe S. It should be just ITS. You're an idiot. Why are you writing a textbook? I'm sorry. That was mean. Textbooks are written by humans. Humans make mistakes. But it just makes me wonder, what other mistakes are they making? Are they making any larger mistakes? I don't know. So, trench, subduction. This is where one piece of the Earth's crust is moving beneath another. And then we have a ridge. Excuse me. That burp finally came out from earlier. So, yeah, here's a ridge. I don't really know what's going on here, but this is all the lithosphere. And I don't know what these arrows are indicating. I guess they're indicating convection heat, which is interesting. I don't know if convection heat would match the definition I gave, which was like the exchange of thermal energy, heat, through gas. I'm guessing not. I'm guessing convection is something else. But maybe not, I don't know. And then a trench. These are two trenches. Same thing. Then we have the mantle here and the asthenosphere. I don't know what the asthenosphere is. This is 700 kilometers here. That's really interesting. Outer core, inner core. Okay. Earth's major tectonic plates and the directions and rates at which they are diverging at seafloor ridges are shown in figure 153. So, are the divergences, or whatever you call them, whatever the noun form is, are they only happening under the sea? Or are they happening at the terrestrial level as well? At terrestrial crust that's above sea level? Are they not happening there? Are they only happening at beneath the ocean and shit? I don't know. Okay. Exercise 1.2, plate. Using either a map of the tectonic plates from the internet or figure 153, determine which tectonic plate you are on right now, approximately how fast it is moving, and in what direction. How far has that plate moved relative to Earth's core since you were born? Gosh, this is going to be a tough one. Where's America? All right, so here's North America. Whoa, this is interesting. This is an interesting map. I've never seen a map like this before. Here's North America, Australia, here's Eurasia. Where's South America? I'm not in South America. I'm just curious. I'm guessing it's here. It's not sure. Oh, wait, no, it's here. This is the Pacific Ocean. Okay. And this is also the Pacific Ocean, but a different plate. And here's South America. Interesting how South America is completely bordered on the left side by a fault, or the edge of a tectonic plate. That's funny. And so is North America right here. And so is some of Africa. So is some of the Arabia. So, no, India's not. Austria is not. Some of Eurasia is at the same part where Africa is. Interesting. Interesting. Very weird. Very strange. Very strange. Okay. So I would be somewhere around here because I'm in Maryland. A map showing 15 of the Earth's tectonic plates, blah, blah, blah. Alright. Plate motion equals 5 centimeters a year. Are they all moving at 5 centimeters a year? I guess so. I guess so. Now, why is this plate moving this way in some parts of it, but this way in others? What's going on there? It's all one plate. Why is it moving in different directions? That's strange. That's very strange. I don't get it. What do the red arrows mean? It doesn't say. I'm just going to ignore them. So if I'm in Maryland, on the Caribbean plate, then, oh wait, North America plate, Caribbean plate. Are these two different plates? Then why do they have the same border? That's weird, but okay. So that probably explains why this plate is moving downward and to the left, and why this over here is moving upward to the left. What in the world? Okay, so I'm moving, my plate is moving 5 centimeters a year. I know that's not a lot, but it feels like a lot. Like, I figured it would be like a couple nanometers a year or something really small like that. Like if continental drift is happening over millions and millions of years, I figured it would be something so small that we wouldn't even be able to, hardly be able to measure it. But 5 centimeters a year, that's half the length of a dilated cervix. That's not all that, I mean, it's small, but that's larger than my finger here, than the width at least. That's like this. It's like this much. I can see it with my eyes, you know? That's weird. Okay. So, if I'm moving at 5 centimeters a year, what's the question? How far has that plate moved relative to the Earth's course since I was born? And how fast is it moving and in what direction? I guess, you know, if the arrow is smaller, that might mean actually that it's less than 5 centimeters a year. So this arrow here would be closest to where I live. And it is smaller. So I guess it's more like 1 centimeter a year. So maybe 1.5. So I'm going to guess it's like 1.5. And so that means I'm 20, almost 23. I'll say 23. So 23 times, I'll say 1.5 is what? 23 plus 11.5. Because 11.5 is half of 23. So that's 34.5 centimeters since I've been born. What the fuck? What in the name of fuck, dude? That's like the length of my forearm, I feel like from here to here. That's so much movement to me. That's like not, I figured it would be microscopic, but it's like this much. Am I wrong? Like, that's like a couple feet, right? Or at least a foot. That's 1/3 of a meter. 1/3 of a meter. So that's like this, right? It's like this much. So yeah, like the length of my forearm. This much since I've been born. And you might be astonished that it's so little, but I'm astonished that it's so much. Sorry for that. Although some of you might have found it interesting. All right, 1.6. Should we look at these? No. We already looked at them. They're just citations. 1.6, geological time. In 1788, after many years of geological study, James Hutton, one of the great pioneers of geology, wrote the following about the age of the Earth. The result, therefore, of our present inquiry is that we find no vestige of a beginning, no prospect of an end. Of course, he wasn't exactly correct. There was a beginning, and there will be an end to the Earth. But what he was trying to express is that geological time is so vast that we humans, who typically live for less than a century, have no means of appreciating how much geological time there is. Hutton didn't even try to assign an age to Earth. But we now know that it is approximately 4,570 million years old, which is what? 4.7 billion years. Using the scientific notation for geological time, that is 4,570 MA for mega annum, or millions of years. Mega annum, or 4.57 GA for giga annum, or billions of years. More recent dates can be expressed in Ka, kilo annum. For example, I'm guessing that's thousands of years. For example, the last cycle of glaciation at approximately 11.7 Ka, or 11,700 years ago. Interesting. This notation will be used for geological dates throughout this book. I'm guessing 11.7 Ka maybe marked the end of an ice age, perhaps, or the beginning of one. I know that there was an ice age around that time, and humans were on Earth, so that's really cool to think about. Exercise 1.3, using geological time notation. This seems boring. Should we do it? Let's just read it and decide whether we do it. To help you understand this scientific notation for geological time, which is used extensively in this book, write the following out in numbers. For example, blah, blah, blah. 2.75 Ka. I'm not going to write, I'm just going to say. 2.75 Ka would be 2,750 years. 2,750 years. 0.93 Ga would be 930 million years. 14.2 Ma would be, I think, would it be 14.2 million years? So 14,200,000 years? Or would it be, no, millions. Yeah, millions of years. Yeah. So 14,200,000 years. We use this notation to describe geological events in the same way that we might say they arrived at 2 p.m. Okay. For example, we can say this rock formed at 45 Ma. So that means 45 million years ago, I'm guessing. Not 45 million years after the formation of the Earth or something, but it could. It could. But this, wait, let's see. It doesn't really say. So I'm guessing it might mean 45 million years after the original formation of the Earth. But this notation is not used to express elapsed time. We don't say, I studied for 4 p.m. for that test. And we don't say, the dinosaurs lived for 160 MA. Instead, we could say the dinosaurs lived from 225 MA to 65 MA, which is 160 million years. Okay, so given this context clue, 225 MA to 65 MA, I'm guessing when you're thinking about, say, 65 MA, that's 65 million years ago. So MA is measured backwards, not forwards like chronological time. It's reverse. Unfortunately, knowing how to express geological time doesn't really help us understand or appreciate its extent. A version of the geological time scale is included as figure 161. Unlike time scales you'll see in other places or even later in this book, this time scale is linear throughout its length, meaning that 50 MA during the Cenozoic is the same thickness as 50 MA during the Hadean. Okay. Huh. What? In each case about the height of the M in MA. What? Oh, it's saying that 50 million years of thickness is about the height of this letter M. So like a little less than a centimeter. See, now that's what I was more so thinking when I was thinking about the continental drift. Like I thought it would be that small, or perhaps way smaller. Now, the Pleistocene glacial epoch began at about 2.6 MA, which is equivalent to half the thickness. So my question is, 50 MA during the Cenozoic is the same thickness as 50 MA during the Hadean. So are MA measured, like is the time chronology of MA relative to the period, to the geohistorical period? Is that how it works? I don't know. I guess we'll probably learn about it. The Pleistocene glacial epoch began at about 2.6 MA, which is equivalent to half the thickness of the thin gray line at the top of the yellow bar marked Cenozoic. I don't know what gray line he's talking about. Yeah, I don't really know what he's talking about. This right here. Wow. Okay, half the thickness of the thin gray line. So half the thickness of this little thin line in 2.6 million years. What in the world, bro? That's nuts. That is so nuts. Okay. Most other timescales have earlier parts of Earth's history compressed so that more detail can be shown for the more recent parts. And that makes it difficult to appreciate the extent of geological time. To create some context, so here's 161, geological time. So we start with the Hadean, which I guess is the first era, 457 million, or no, 4,570,000,000 years ago this happened. Archean, 3.8 billion. What the hell? Is it called Archean because of the domain of species, the domain of organisms called archaea? There's bacteria, archaea, and no, there's protozoa, archaea, and eukarya. Those are the three domains, I believe, of life. And archaea is a single-celled domain of organisms. And then protozoa is that right? I think it's right. I'm a little rough on my biology, but I'm pretty sure that's right. It's protozoa, eukarya, and archaea. I'm almost certain. Protozoa is like bacteria and other stuff. Archaea is also single cell, but it is its own domain for some reason. And then eukarya is the protists, which is another type of single-celled and sometimes multicellular organisms. They're very small, but it also includes multicellular life, such as us. We belong to domain eukarya. Anyway, that was an aside. Then we got Proterozoic. This might have something to do with protozoa. What the hell? My bad. Oh, god damn it. It's fucking shit. Sorry. Okay. And let me make that big. Okay. So Proterozoic. And all of these first three are encompassing billions of years. This one is like 2 billion years. All this. This one is 1.3 billion. This one is 800 million. What the fuck, dude? And then these are all less than 500 million. Paleozoic seems to be only 100 million or so. Maybe, no, more like 200 million. Mesozoic seems to be something along the lines of 100 to 200 million, and Cenozoic seems like it seems even less than 100 million. So compared to these would be way bigger, I think. Let's read about this again. Unlike timescales you're seeing other places or even later in this book, this timescale is linear throughout its length, meaning that, okay, so this is actually accurate. This is actually an accurate visual representation of how long each time period lasted. Like, the Proterozoic, compared to all these three, absolutely dwarfs them. That's insane in terms of time scale. What the fuck? To create some context, the Phanerozoic eon, the last 452 million years, is named for the time during which visible phanerous life, zoe, is present in the geological record. In fact, large organisms, those that leave fossils visible to the naked eye, have existed for a little longer than that, first appearing around 600 MA. I'll call it Ma. Should I call it Ma? Or a span of just over 13% of geological time. Oh, and that's this eon right here. Okay. Animals have been on land for 360 million years, or 8% of geological time. So, for the first, 87% of Earth's history, there was no life that was visible to the naked eye. The first 87%. That's incredible. Incredible. Wow. Okay. Mammals have dominated since the demise of the dinosaurs around 65 MA. That would maybe be the beginning of the Cenozoic, or 1.5% of geological time. And the genus Homo has existed since approximately 2.8 MA, or 0.06% of geological time. 1/1600th of geological time. Oh my god. And that's not even considering Homo sapiens. That's just the genus Homo, including Homo erectus, which is very far, probably closer to monkeys than to us. So Homo sapiens is probably way less. That's probably more like 200 Ka. So that might be something like 0.005%. That would be my guess. I don't know if that's right. What the hell? I've heard about that before, but just reading it in this textbook makes it just as surreal as it was the first time I heard about it on the internet. Geologists and geology students need to understand geological time. That doesn't mean memorizing the geological time scale. Instead, it means getting your mind around the concept that although most geological processes are extremely slow, very large and important things can happen if such processes continue for enough time. For example, the Atlantic Ocean between Nova Scotia and northwestern Africa has been getting wider at a rate of 2.5 centimeters per year. Imagine yourself taking a journey at that rate. It would be impossibly and ridiculously slow. And yet, since it started to form at around 200 MA, just 4% of geological time, the Atlantic Ocean has grown to a width of over 5,000 kilometers. Excuse me. A useful mechanism for understanding geological time is to scale it all down into 1 year. The origin of the solar system and Earth at 4.75 or 4.57 GA would be represented by January 1st. And the present year would be represented by the last tiny fraction of a second on New Year's Eve. At this scale, each day of the year represents 12.5 million years. Each hour represents about 500,000. Each minute represents 8,694 years, and each second represents 145 years. Some significant events in Earth's history. So, yeah, if you put your existence into 1 year relative to the rest of Earth, relative to the age of Earth, it is less than a second. If you're putting it all in the scale of 1 year, less than a second. Wow. Yeah, that's nuts. That's nuts. That might give you a bit of an existential crisis. But if you're looking at the origin of all life, this is kind of an argument that Hank Green makes that I kind of like. If you're looking at the origin of all life, that has existed for, I think, since near the creation of Earth, near the formation of Earth. So, kind of a third of the age of the universe. So that makes it a lot bigger. Like we are part of something very big, which is life in general. And it only exists here, as far as we know. Some significant events in Earth's history as expressed on this timescale are summarized on table 1.1. Where's that? Here we go. Table 1.1, a summary of some important geological dates, expressed as if all of geological time was condensed into 1 year. Formation of oceans and continents, January. Evolution of the first primitive life forms, early March. So that's most of the existence of the world. And I'm guessing that those first primitive life forms were very different from the single-celled organisms that exist today, especially when you consider the idea that those organisms have a much faster feedback loop for evolution, so they change much quicker. So they had to have been way different from the bacteria and archaea that exist today, the protozoa and archaea that exist today. Okay. So, or wait, is bacteria one of the domains? It might be. I might be wrong. Anyway, formation of British Columbia's oldest rocks, because this is a Canadian textbook. Has to say that, I'm guessing. July. Excuse me. Doesn't have to say that, but it wants to. That would happen in July. Evolution of the first multi-celled animals. November 15th, near the end of the year. Animals first crawled onto land on December 1st, the last month of the year. The beginning of the last month, but the last month. Vancouver Island reached North America, and the Rocky Mountains were formed. That would be December 25th. Extinction of the non-avian dinosaurs, December 26th. Wow. Beginning of the Pleistocene Ice Age, 8 p.m., December 31st. Incredible. Retreat of the most recent glacial ice from southern Canada, 11:58 p.m., December 31st. Arrival of the first people in British Columbia, December 31st at 11:59 p.m. Arrival of the first Europeans on the west coast of what is now Canada, and I would assume also the arrival of Europeans to North America, where I live, 2 seconds before midnight, December 31st. Nuts. Exercise 1-4, take a trip through geological time. We're going on a road trip. A woad twip. I almost said woad twip. Pack some snacks and grab some of your favorite music. We'll start in Tofino on Vancouver Island and head for the Royal Tyrrell Museum, just outside of Drumheller, Alberta. Blah, 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 blah. Am I really going to go into this? I'm not from Canada. I'm not from here. Of course, it's just a virtual road trip, but it will be fun anyway to join in, go to virtual road trip. Once you've had a chance to do the road trip, answer these questions. I don't know. I don't think we're going to do that. It's a little too Canadian for me. Figure 161, image description. I think we already looked at that. Yeah, that's just the citation. Yeah. We've reached the end of the chapter. Summary. The topics covered in this chapter can be summarized as follows. I'm not going to read that summary. So, we're done. We read the whole chapter. Huzzah. I'm going to make my face bigger. So, thank you for watching. My name is Luke. This is Castles in the Air. That was an incredibly fascinating chapter. That was really interesting stuff to read about. I feel a lot smarter, and I have developed even more of an appreciation, a much greater appreciation for geology and the significance of it. And I hope you enjoyed. I'm going to put a playlist in this end screen for all of my geology videos. This is obviously the first, but there will be more for certain. And you can follow that playlist to see what new videos I make, and it should pop up in your notifications or like your subscriptions or something. Or you could just subscribe to the channel. You could do that, but I don't really care, to be honest. My name is Luke. This is Castles in the Air. This channel is called Castles in the Air because I have so many lofty ambitions that seem so out of reach and feel so out of reach to me that it feels like I'm building castles in the sky with no foundation beneath them. Seems impossible sometimes. And I like it anyway. I enjoy myself anyway. I study geology. I study all other kinds of science and intellectual fields. Math, physics, chemistry, engineering, coding, programming. I also play a lot of different sports, and I want to get good at a lot of different sports. I haven't made many videos about that, though, because sports, a lot of them cost money. and I haven't been able to play them that much because I've been broke as fuck. But I did get a new job, so yeah, that's an aside. And a lot of creative fields as well, like music. I have a concept album I'm working on. I have a movie that I'm writing, a screenplay that I'm writing. Same thing. I'm writing a comic book. There's a lot of other shit too. So yeah. My name is Luke. This is Castles in the Air. Goodbye.